Evet. Ee, Hoş geldiniz tekrardan. Ben öncelikle Tolga Hocama, Mehmet Hocama davet için çok teşekkür etmek istiyorum. Bizim için gerçekten çok değerli bir ziyaret oldu sizlerle olmak. E, Ben bugün biraz enstitüyü, oradaki merkezleri anlatacağım. Daha sonra da yaptığımız çalışmalarla ilgili bilgi vereceğim. 25 dakikada yaklaşık toparlamaya çalışacağım. Sizlere de fazla sıkmadan. Şimdi Mehmet Hocam'ın aktardığı gibi ben fiziksel oşinograf olarak eğitim aldım. Daha sonra ODTÜ Deniz Bilimleri Enstitüsü'nde çalışmalarıma e, devam ettim. Bu arada ODTÜ'de e, Deniz Ekosistem ve İklim Araştırmaları Merkezi'ni kurduk, DEKOSİM. Bu bizim enstitünün en kritik altyapı desteğini sağlayan projemiz. Onun dışında e, yakın zamanda ODTÜ İklim Merkezi kuruldu. Tabii enstitü bu yıl 50. yılını kutluyor bu arada. Sizleri de farklı etkinliklerimiz olacak. Onlara bekleriz, davet edeceğiz. Bizim amiral araştırma gemimiz, bilim araştırma gemimiz. O da 40 yaşında şu anda. Yani emektar bir gemi. E, Enstitüye gelecek olursak, dediğim gibi 50 yıldır tüm ulusal denizlerde biz deniz bilimi araştırmalarını yürütüyoruz. Bilimsel anlamda üretken bir kurum, enstitü. Aynı zamanda projeler konusunda da oldukça üretken. Dediğim gibi tüm Türkiye denizlerinde çalışmalarımız mevcut ama bunun ötesinde kutuplar, hatta Mustafa Hoca'nın anlatacağı gibi derin denizlerde de çeşitli çalışmalar yürütüyoruz. Ana kapsam bizim tabii ki bir oşinografi enstitüsü esasında. Örneğin Avrasya belki daha interdisipliner. Biz de oldukça interdisipliner bir yapıdayız ama daha çok oşinografi çalışmaları altında e, bu interdisiplinerlik sürüyor. Oşinografi bizim şemsiye departmanımız. Onun dışında Marine Biology and Fisheries ve Marine Geology and Geophysics diye iki bölümümüz daha mevcut. Tabii ki enstitü mükemmel bilim, temel bilim üretmek üzerine çok uzun yıllardır tüm bu disiplinlerde çalışmalarını yürütüyor. Buna ek olarak son zamanlarda mavi ekonomi, deniz bilim stratejileri, deniz ekonomi stratejilerinin geliştirilmesi konularında da yoğun çalışmalar yürütüyoruz. Enstitünün vizyonunu oluştururken hem ulusal hem uluslararası farklı tabii ki vizyonlardan faydalanarak bunu yapıyoruz ve sürekli de kurumu buna adapte ediyoruz. Yani bizim bir bilim stratejimiz var. Buna yönelik çalışmaları şekillendirmeye çalışıyoruz. Bunda da belli bir başarıya ulaştığımızı ölçüyoruz şu anda. Belli enstitünün en büyük yani enstitünün motoru diyeceğimiz kaynaklar daha çok uluslararası projelerden geliyor. Özellikle Avrupa Birliği projelerinden gelmekte. Koordinatörlük yaptığımız projeler var. E, Mustafa Hoca anlatacak, ERC'ye ev sahipliği yapıyoruz ve birçok projede de ortaklığımız mevcut. ODTÜ İklim Merkezi'nin ana kurulma amacı ODTÜ'deki iklim değişikliği ile ilgili farklı çalışmalar arasında bir sinerji oluşturmak. ODTÜ işte iklim değişikliğine yönelik teknoloji geliştirmede, politika üretmede, şehirlerle ilgili yaptığı çalışmalarda ve temel bilim çalışmalarında oldukça başarılı bir üniversite. Ama bu yapılan çalışmalar arasında bir kopukluk, bir sinerji eksikliği vardı. Bu sebeple bir çatı olarak kuruldu ve deniz bilimlerinden doğdu. Çünkü deniz bilimleri olarak biz en çok iklim değişikliği ile ilgili çalışmaları yapan bölüm olduğumuz için deniz bilimleri ev sahipliğinde esasında şu anda yürüyor ama e, bu da deniz bilimlerine yeni bir açılım, deniz bilimlerinin daha kapsayıcı, yani üniversite içinde daha kapsayıcı bir role çıkarmış oldu. Hem Ankara'da bir yerimiz var hem de Mersin kampüsümüzde bir yerimiz var. Bu arada biz Mersin Erdemli kampüsünde bulunuyoruz. Herkes biliyordur diye ondan bahsetmedim ama e, Dekosim binamız bu arada Mehmet Hocam tamamlanmak üzere. En son gördüğünüzde inşaat halindeydi. İnşallah birkaç aya onun da açılışını yapacağız. Dekosim deniz bilimlerine adanmış bir laboratuvar binası. Oldukça donanımlı olacak. Bunun ötesinde denizlerde uzun süreli ölçümler yapabilmek üzerine tabii farklı cihazlar hem geliştiriyoruz hem de bunları alıp kullanma yönünde kapasite geliştiriyoruz. Mesela sabit sistemler, şamandıra sistemleri gibi burada gördüğünüz. Ops, ben bunu nasıl becerdim? Evet, bunun neyse ben dokunmayayım fazla. İşte şamandıra sistemleri ya da insansız deniz araçları gibi araçları da uzun vadeli ölçümler yapmak için kullanıyoruz. Dekosim'in ana kuruluş amacı hem denizleri uzun süreli gözlemlemek hem de denizlerde bir öngörü kapasitesi oluşturmak. İşte burada Avrasya'da da bu kapasite oldukça güçlü. Bu öngörü kapasitesini nasıl oluşturuyoruz? Daha çok modeller vasıtasıyla tabii ki bu çalışmaları yürütüyoruz. Dekosim'in ana modüllerine bakacak olursanız işte temel araştırmalar, işte e, zaten laboratuvarda çeşitli ölçümler, araştırmalar yapılıyor. Bunun dışında işte mezokozum ölçeğinde ya da daha ufak mikrokozum ölçeğinde çalışmaları da yapıyoruz. Deniz çalışmalarımızın tabii ki ana vasıtası gemiler ama bu gemilerde de birçok teknolojiyi kullanmanız gerekiyor. Sabit sistemler oldukça önemli. Son dönemlerde bunları geliştirme yönünde ciddi bir gayret içindeyiz. Ve demin dediğim gibi öngörü sistemlerinin geliştirilmesi ve bunlara ek olarak da karar destek sistemlerinin geliştirilmesi yönünde Dekosim altında çalışmaları yapıyoruz. Şimdi bundan sonra biraz İngilizceye geçeceğim izninizle. Sunumun geri kalanında e, during the rest of my talk, I would like to focus a little bit on our research that's going on blue economy and the strategies we developed there, and also the digital twins of the oceans. I thought this would draw your attention. And then, if I have some time, I will talk about the regional cooperations that we have been carrying out. Uh, as I said, our institute's main focus is oceanographic research, but more and more recently, we are focusing on how we can develop some solutions for the blue economy. And of course, this includes combating the pressures on the marine ecosystems. At the moment, most of the marine ecosystems, especially the ecosystems that surround our seas, are under many different pressures, starting from climate change to pollution to overfishing to invasive species. And one of the ways to develop solutions is, of course, basic science. You need to know these ecosystems to be able to develop solutions for these systems. And these need to be supported with innovations, input from the policy, and it needs to be supported with technology. Otherwise, it's not possible to develop these solutions. So I think these are the facts that you already know, but we have gathered these together, how marine ecosystems and blue economy contribute. But when you look at the blue economy sectors, actually they are, you can divide them under two pillars. One of them is the sectors that are already established. For example, tourism or fisheries are already established sectors, but even these sectors has many limitations that need solutions. For example, climate change or management methods for fisheries, for example. But on the other hand, there are sectors that are emerging, like biotechnology, offshore energy farms, and even new methods of aquaculture are emerging sectors. And these sectors definitely need a lot of knowledge that we need to develop. And there are different approaches to these challenges, but one of the ideas that we have developed is multi-use ocean platforms. And under this idea and under this project, we have worked together with Mehmet Hoca. Multi-use ocean platforms are an emerging concept for developing ocean technologies. And in many countries, there are different systems that are focusing on this. For example, hybrid systems on solar systems together with wind systems and aquaculture, or more and more hydrogen extraction directly from the sea is nowadays practiced. And we put together a consortium that would develop the technologies that would go beyond the existing technologies. And this is a quite a strong consortium, and the project is under evaluation at the moment. But when you look at the idea behind this project is that first of all, you need to design and establish these platforms, because that's not easy. There are many different modules on this platform that needs to function in a synergistic way. So we propose to develop different designs for different Turkish seas, and then development of energy systems like offshore wind, solar energy, hydrogen from the seawater, extraction of valuable elements from the sea, and also biotechnology from different organisms. These include extraction of drugs, proteins from the marine algae. But what we propose to do in collaboration with Mehmet Hoca is observation data and digital support systems. And there we have proposed to develop a digital twin that we were going to develop the digital twin of the whole ocean region, but this would support all these systems, both how these systems affect the seas, but also how the environmental conditions will affect how these systems would function. I'm not going to go into the detail of different modules, but if you're interested, we can discuss more. But when I come to Pillar 5, a digital twin does not only compose of models, but you also need continuous data. So to access to this data, you need to use some fixed systems, some unmanned vehicles, and also some unmanned vehicles under the sea. So that's what we have proposed to be able to observe continuously this fraction of the ocean and develop the digital ocean in the digital world. So how do we develop these digital oceans and how do we use them? I will show you two examples from Marmara and the Black Sea. So digital oceans, digital twins nowadays can be used in health sciences, in environmental sciences. When we talk about the digital twin of the ocean, of course, the challenge is big, because when you are developing the digital twin of an instrument or of a city, it's much easier because there's continuous data flow. So you know what you are producing, because the data is there. But when we are talking about the ocean, the data is generally quite poor. We don't know every single point of the ocean, and it's very hard to get continuous data. The physics of the ocean to a certain extent, but when it comes to ecology, it's almost impossible. Our knowledge is very limited, but still, digital twins are a good way to start understanding these systems and to start testing different what-if scenarios, for example. And there is the EDITO system, the European Digital Twin Ocean, which focuses on testing different what-if scenarios. And for example, we have started with Marmara under the Marmot project, because as you may know, there are many pressures that are acting on the Marmara ecosystem. And at the moment, actually, there's the mucilage going on in the Marmara Sea. However, the main problem in the Sea of Marmara is deoxygenation, and the reason of it is pollution. Of course, all these are anthropogenic. And to understand the state of the sea and to develop solutions, we needed this digital ocean, digital twin of Marmara. And Marmara is a very complicated system. It's not so easy to understand it and then to develop the digital twin. Marmara has been warming up for a long while, and its oxygen levels has been depleted for a long while. What you see on the left is how the oxygen levels has changed over the last few decades. And here you may see it better. The whole basin has become more and more poorer in terms of oxygen levels. This is the main problem in Marmara. Mucilage is what you see at the end, actually, but the problem is always there. So the Marmot project focuses on how we can increase these oxygen levels in the Sea of Marmara. I guess I will not go into detail while these oxygen levels go down. It's mainly pollution in Marmara, and at the end we started seeing the mucilage event more and more often. For example, these are some turbidity measurements. On the right bottom, you see just from last month when we were in the cruise in the Sea of Marmara. So mucilage was widespread, although the concentrations are nowhere near to what happened in 2021. But still, in the whole basin of Marmara, we have witnessed the mucilage event. So to tackle the challenges in Marmara, of course, we continue our cruises in Marmara, and we have some fixed systems in Marmara where we are getting the data. But to test different what-if scenarios, we need the digital twin. So what we did, we have developed a model, an ecosystem model that's specific to the Marmara ecosystem, because it's very complicated. You cannot just adapt any ecosystem model to Marmara. And this model was quite complicated. It includes cycles of many different elements, and several phytoplankton, zooplankton, even fish species were included in this model. Of course, the basis of these models are the physical dynamics. So we have adapted the NEMO model to Sea of Marmara. Actually, this is a movie, but I don't know if it will work or not. And then after developing the physical model, on top we have coupled the ecosystem model, and we have started doing some tests with this ecosystem model. So we still need to continue with our runs to test all our what-if scenarios. But one of the main questions is how much we need to reduce the pollution levels in Sea of Marmara to start having oxygen levels beyond a certain threshold. And here we have decreased the levels of pollution from different point sources or from river sources to understand if it will help. With 50% decrease, for example, we see that the oxygenated water from the Mediterranean Sea helps quite a bit, although this will take decades until the oxygen levels reach to levels that we aim for. So most likely we need mitigation procedures which goes beyond 50% of decrease in reduction in pollution levels. And yeah, we collected data from gliders in the Sea of Marmara, which is quite interesting. It's still under process, and same with scamfish. We have been collecting these data. And this is where the main pollution sources are. The point sources are mostly from Istanbul, but when it comes to the river sources, it's mostly from the Susurluk area. So we are testing how these different sources are affecting the sea and developing solutions for a healthier Marmara. And in the Black Sea, our efforts are a little bit further than the Sea of Marmara. So this is the last thing I will show on the digital twin. So Bridge Black Sea project is a Horizon Europe funded project that we are coordinating. And the main aim here is to develop a safe operating space in the Black Sea. And this has three different modules. The first one is service dynamics, understanding the ecosystem of the Black Sea, the blue growth incubators, and empowered citizens. So the main aim is, as I told you, to understand the boundaries of the ecosystem in the Black Sea and how different sectors should take action so we respect these boundaries. And this is not very easy, actually. Even with a digital twin, this is not very easy to assess. So I will tell you how we did this. First of all, we have established the knowledge base. So we have gathered all the data that's available in the Black Sea, linked different databases. Then we have different partners developed their own models. So we ran an ensemble of models to better understand the uncertainties, and different models addressed different blue economy sectors. For the first time, we have done the resilience analysis in the Black Sea, and we have developed some adaptive management tools. So the knowledge base also includes the socioeconomic data in the Black Sea and different scenarios. So there we have developed different scenarios, socioeconomic scenarios, and with the models, we are testing these different scenarios. The modeling system in the Black Sea is similar to what I have shown in Sea of Marmara, and the resilience analysis is done on both using the data and the model results. And the adaptive management solutions include an AI-based risk-based assessment tool and a cumulative effect assessment tool where we have assessed the effect of all the pressure in the Black Sea. And in a way, this is a tool towards planning. And maybe you have heard about marine spatial planning. So you need to apply such analysis to understand how you can better plan the sea space. And in the bridge project, we have different pilot sites where we have carried out both observations and modeling studies, and also we have established living labs, and we have focused on the effect of different sectors and tried to understand the services that the seas provide in these different regions. And we have done different scenario analysis with the models, including the effect of climate, assess the good ecosystem status indicators in the Black Sea, and carried out resilience assessment in different parts of the Black Sea to understand the resilience of the ecosystem under different pressure and to understand the limits of the ecosystem. And the adaptive management tool that we have developed is quite advanced, and at the moment we are building the digital twin ocean on this mechanism actually, which I will show you. And in another work package, we have developed and utilized different smart observation tools in the Black Sea. Mustafa Yücel is the work package leader in this here. And yeah, we have a Black Sea database which you can access. And we are trying to link this with the Digital Twin Ocean portal. And beyond these observations, different analysis, we are also organizing different summits, for example, the high-tech summit. So to understand what's the potential in the Black Sea area. And so far, more than 50 potential startups has applied to this, and we have supported several of them. And in terms of science policy dialogue, we have organized different forums, and also in terms of capacity building and education, we have our efforts going on. And we will have different webinars towards the end of this project. Please follow the project website or the social media, and please join our seminars. And one of them will be on observing technologies, and the other one will be on digital twin. And the unique thing about the digital twin demonstrator for the Black Sea is, as you see here, what we are doing is that we are combining data models with machine learning and with decision-making tools. So the core of the digital twin here is the decision support tools. And on top, we are supporting this with resilience assessment and, again, AI-based planning tools. So this is part of the European Digital Ocean Forum already, and we are planning to establish some new projects on this framework for all the European seas. So we are planning to extend this to all the European seas. So these are some results from the Black Sea, but maybe I can stop here. Just a snapshot of our model structure and our modeling results in the Black Sea. And similar to what Mehmet Hocas are doing, we are doing forecasting in the Black Sea, including the different ecosystem compartments, including the fish. And we are testing different scenarios, socioeconomic scenarios. These are both SSP scenarios, but also how pollution changes in the Black Sea, how plastic pollution changes, and fisheries, and in terms of aquaculture development. So this is a combination of both climate pressures and how other pressures are changing and how these are affecting both the ecosystem and different services that the seas provide. So I think I will stop here, and we can discuss later on if you have any further questions.
Tamam, şey. Evet, iyi öğleden sonralar. Tekrar teşekkür ederiz Tolga Hocam, Mehmet Hocam, Nazlı Hocam, bütün hocalarımız, enstitünün değerli üyeleri. Ben de hani çok uzun tutmamaya çalışarak soru cevap belki interaction'a vakit ayırarak sizlerin de zaman daha çok almadan hızlıca son daha ayağımızın tozuyla döndüğümüz bir seferin bazı sonuçlarından bahsetmek istiyorum. Yani ilk olarak ilk bir sunum olmasından dolayı hani çok ham düzeyde sizinle bir paylaşım yapacağım ama bu daha 3 hafta önce olan bir seafloor eruption olayı. Bu vesileyle de İngilizceye döneyim. As Barış also mentioned, we've been doing different projects in our institute, and one of the projects funded by the ERC, European Research Council program, we turn our attention to deep sea, to different seafloor systems. Before that, I'm originally a chemical engineer, then studied chemical oceanography, so I'm more like observational person spending time on ships, taking samples, or using different vehicles, including manned submarines, to really sample and also sometimes put sensors, recover sensors. So in a way, I think some of you are doing similar work in that regard. And then we do a lot of joint work with modeling experts like Barış and other experts in our institute and abroad to really integrate our results to both to develop new models, but also to improve existing models. Okay, so actually today I'll focus on a very specific event that we witnessed in our latest expedition in the Pacific Ocean, which I will come to in a minute, but let me first just show you the event itself. And so maybe many of you are familiar with deep sea hydrothermal vents. These are places where hot water coming from deep sea volcanoes or modulated by deep sea volcanism, they are actually injected back to the deep ocean in chemically transformed way. So they come back warmer than a deep sea environment. They are laden with energy-rich chemicals such as methane, hydrogen sulfide, and then you find this type of biology around these hydrothermal vents. So this particular footage is from East Pacific Rise, and just from 3 weeks ago, from about 2,520 meters. So it's dark over there, of course, it's high pressures, and the only energy source that's feeding all these creatures here, it's the chemistry, basically, chemicals that are coming from the deep sea volcanoes. And here in this picture, you see our deep sea electrochemical sensor, which is capable of measuring some of the species, chemical species that are of interest for this biology. So in this very place, actually, this footage is from April 28th, which is 3 weeks ago, and on April 29th, when we dove with the submarine to the same place, this is the picture that we encountered. So this was actually hours after an eruption, seafloor eruption. I don't know if we can hear the sound as well, but the divers reached there with submarine Alvin, hoping again to find tube worms, mussels, and those sort of species. We had further work to do on those organisms, on different fluids that are feeding. But this is actually very close, almost the same location as what I have shown previously. So this particular hydrothermal vent is called Tika. It's kind of, maybe you have heard different deep sea ecology theories about succession or different things. And then this is actually where most of those theories have been studied. Kind of one of the signature sites in deep sea ecology. And it's all gone, actually. All organisms that were there just day before, and everything else is gone. And maybe you also notice in the footage
there's no way there's
some hot magma showing up as well. And that's exactly when you hear the pilot's voice here. And she's now immediately talking to the ship after seeing escaped those hot magma.
It's gone.
She's basically saying that it's gone. The whole thing is gone. So so we captured an eruption hours after. You may be saying that, okay, what's the big surprise about that? Because it's already a mid-ocean rich, fast-spreading rich center, and then of course you hope to encounter eruption. But an eruption, a seafloor, a deep seafloor eruption, let's put it that way, has never been captured so rapidly after the event itself. So it was the first time that we were able to sample fluids or rocks. Of course, there was no more biology to sample, but it gave us that opportunity. So I'll come back to this discovery again, but let's take a few steps back and let me explain why we were there at all. Actually, we had a joint project with colleagues in the USA on different aspects of hydrothermal vent systems, one of them being hydrothermal systems modulating ocean carbon. And another aspect was actually how these hydrothermal systems produce different tracers, actually, which can be detected and which can be of astrobiological significance. So ocean worlds in the solar system, it's the new or emerging kind of target of life exploration or habitability exploration by both NASA and European Space Agency. Ocean worlds have been a target. For NASA, I'm not so sure anymore. But at least the mission is flying there. I don't think Trump will invite the instrument back. It's already flying, so it's better arrive there, collect data. But Europa is one of them. There are many other ocean worlds covered with ice, but in their interior, most likely they have saltwater oceans. So in the seafloor of those saltwater oceans, it's predicted that these bodies are volcanically active. So just as our deep sea volcanoes on our oceans, in our oceans, there's very likelihood that there's also hydrothermal vents, volcanoes in these deep oceans. How do we know them? Especially Europa and Enceladus, they have plume-like, geyser-like structures emanating from their icy shell. So it shows us that there is some activity going on in the seafloor. And Nazlı Hoca is also working on this topic with SEDA, where I'm also a committee member, approaching the issue from a more modeling perspective. And our approach is more, how can we use the Earth analogs of these ocean worlds, or at least the habitats of those ocean worlds, how we can use Earth analogs of those systems to understand how to study the habitability of those worlds using the Earth analogs, basically. So hydrothermal vents are basically, they tend to exist along mid-ocean ridges or subduction zones. Basically, superheated waters up to 400 degrees Celsius, depending on pressure. They are emanated into the deep ocean. The surrounding seawater can be, if you're in the deep Pacific, it's most likely 2 degrees Celsius. Maybe in deep Atlantic, 4 degrees, but nothing more. So the temperature gradient is huge. And yeah, one of the aims of our project is to study the particle signature of these sort of hydrothermal vents in different parts of our oceans. And because one of the ideas is ideas of the new missions flying to Europa, for example, is to be able to characterize the plume of Europa. Well, any plume that can be emitted through the ice cracks, to characterize the particle chemistry, also gas chemistry. But if there are particles, they will also characterize the chemistry. And then from all that chemical composition, they will try to infer the chemistry of the interior ocean, or the nature of the hydrothermalism, if it's there, etc. So here we are trying to provide to the especially planetary science community a kind of reverse approach where we study different deep sea habitats, and then we actually show what sort of particles they generate, how they differ from each other, and we try to propose a framework that they can use and they can cite hopefully when they publish their papers in 2030s. So oceanography, in a way, is becoming also important in planetary science or space research because of these icy moons and the very thick oceans that they contain. And there are now some papers emerging that the physical oceanography of these oceans, of course, data are very few. It's a lot of assumptions, right? But it's likely that there are large-scale convections in these oceans, which may bring these deep-sea products to the surface under the ice, which can then be emitted and detected. So that's pretty much our ERC project to basically conduct new oceanographic research to guide upcoming exploration of the ocean worlds. All right, I want to direct you to a newly published paper by us. This paper has just actually come out about 10 days ago, and it's kind of summarizing the core concept of the project, also proposing some new framework. You can also find it in the Planetary Science Journal. It was also a first for us because as oceanographers, we published our work in a Planetary Science Journal, so we are trying to speak to them and attract their interest. So I think it worked very well. All right, so within that within our project, maybe it's too little here, but there are some different case study sites, Black Sea, Marmara Sea, East Pacific Rise, Mid-Atlantic Ridge. So we are not only working on deep sea hydrothermal events, but also places like Black Sea due to their anaerobic character. But in this talk, of course, I'll focus on the hydrothermal systems. So yeah, our expedition was with the research vessel Atlantis of the United States, operated by Woods Hole Oceanographic Institute. But over there, when you write a project, your project is funded, you can use a ship basically for the allocated period. Also, if you are interested in deep sea research, you can also apply for deep sea submarine dives, and then once your project is accepted, they also come within the package. So it's quite nice. And we had 22 dives in this expedition. We lost 3 dives due to some weather or technical issues, and the last 2 dives were canceled because of the eruption. Because after seeing that hot magma hanging around, they decided, okay, we are coming back, and at this dives of that expedition were over. But the team members were quite young overall. For the majority of the team members, it was their first ever deep sea cruise, and for some of them, it was their ever first marine expedition. So a lot of new people meeting with deep sea science in this expedition. So I kind of felt old because my first dive with Alvin, for example, happened in 2007. So and then over the years, we use different platforms, ROVs, Nautil also, where members or past members of this institute, they dove with Nautil in Marmara, I think. But anyway, what was special about this expedition is that we were able to, thanks to the ERC funding, we were able to actually take a good number of Turkish students and scientists with us, and all of them had a chance to dive with Alvin, and we have a cruise blog. I forgot to put the link here, but the details are there. We are putting in basically some impressions from the expedition, and their own experience from their own words are also in that blog. So that was another important aspect of this expedition. Actually, now it's not only me anymore, but more people have already met with deep sea science, and one of them is, Nazlı is pointing out, Hilal is your graduate master's, and then she came to METU IMS after her master's for PhD. So actually 2 institutions, they're already working together in different formats. And we hope to increase that actually. Anyway, this is our study site. Maybe the map is small, but this is Central America. So it's about 5 days of steaming from Costa Rica. You reach the East Pacific Rise 9 degrees north. So that's the shorthand notation of the area. And then after our expedition, we actually sailed all the way to San Diego. Took about 6 days. So a lot of time on the ship. Usually these sort of expeditions, you are actually covering a small area, because the submarine, when it's diving, when it's down there, it can maybe go, it can cover maybe a couple of kilometers, 1 mile, nautical mile, that's it, in terms of battery power. It can do a little bit more if you're not doing a lot of manipulative work with the arms. But if you are doing a lot of sampling, a lot of work with robotic arms, then you are limited. So usually one dive is allocated to one particular vent location. So here you see our vent locations, such as BioVent, TICA, Bio9, P-Vent. These are different vent structures, basically. When you go down there, there's usually a main central chimney emanating fluids, but there are also a lot of diffuse flows with biology around it. Of course, now probably they're all gone. But so this is the basket of Alvin, submarine Alvin, and in this particular expedition, we sampled a lot of water coming from hydrothermal vents. So we had this titanium water samplers. In this particular photo, I think you see 3 pairs. 3 more pairs are on the other side. And we also had our electrochemical sensor that we acquired from our ERC project attached to a wand like this. So it can be manipulated and put over biology or over some rock. So there are electrodes basically at the at the end of this wand, and the whole thing is connected to this titanium bottle which houses the electronics. So this system used to be really big. 2 people used to carry it, and then it was a mess to really attach. But now things are getting smaller, especially electronics. So things are miniaturized, so you can actually it takes less space in the basket. Why we use, for example, this type of tool? The organism you see also in the video, such as this one, Riftia pachyphylla, it's a tube worm. Actually, it feeds on a redox gradient. It lives in a mixing zone, a very dynamic mixing zone where oxygen and sulfide are mixing up. So it's very important you can take a sample from the mixing zone, but since it's already mixed, it's a mixture of different fluids, things will change even in a few minutes. So it's very important to do as much as you can as in situ sensing in these sort of dynamic habitats. Anyway, what's happening here is chemosynthesis. Maybe not much time to discuss this today, but it's in a way like photosynthesis, but without water. Instead of photosynthetic organisms splitting water, chemosynthetic organisms, they split hydrogen sulfide. So H2O becomes H2S. Actually, both chemosynthesis and photosynthesis, the organisms are interested in hydrogen. That's the main driving force of the carbon fixation mechanism. In photosynthesis, oxygen is a waste product, and in chemosynthesis, sulfur, different forms of sulfur, is a waste product. So we have collected many different data sets with the tool over different habitats. Just skipping them. We came back with lots of fluid samples, which we will be working on in the next few months. But just to show you some of the first results, here temperature versus pH of different fluids that we sampled. Now these are the sample data. These are real high temperature fluid samples. First results on them at least. Usually the lower pH are associated with higher temperature fluids. So these fluids, actually hydrothermal fluids, are much more acidic than the surrounding seawater. So that's actually, in the context of ocean acidification, I think some of you are interested in that. These habitats are already acidic, and these organisms are already adapted to really harsh acidic conditions, in addition to pressure and all kinds of other things. Yeah, on the right, you see temperature versus sulfide. Again, higher temperature fluids, they are closer to this volcanic source, so they are enriched in sulfide. But we noticed one outlier in both data sets, and that's the Tika sample. So that's the area where the eruption happened. That's the sample sampled right before the eruption, the day before the eruption. So what's showing, actually the fluids themselves, they were already giving a sign of the eruption. They were already much lower in pH than expected, and their sulfide values was really skyrocketing, meaning that volatiles are really, it's really boiling. Well, they call it phase separation. Geophysicists call it phase separation, but basically it means that when that happens close to an eruption, the fluids become even more enriched in volatile species such as hydrogen sulfide, CO2. So we have captured this actually at the day before, and then, yeah. When we started the expedition, we knew that actually this place was going through a eruption cycle of 15 to 12 years, but there's of course some uncertainty in these predictions. And as of 2025, 18 years have passed, and we knew that an eruption was imminent, but we didn't know that actually we would be the ones actually to dive right over it. So that's essentially the video that you showed. I can show it again, and it is literally 16 hours later of the
video to anything we can.
Basically everything is gone. All biology is wiped out. So what's going to happen in the system is that because we know how this system changes after an eruption, we already documented 2 eruption cycles, and now a 3rd one is happening. Now what's going to happen probably in the next few months is bacteria will colonize these newly formed hot areas. Then a kind of precursor colonizer Tevnia tube worm will come and colonize a whole lot, and then it will be replaced or outcompeted by this larger tube worm called Riftia pachyptila, which will be in the end give some place to mussels or other peripheral organisms. So that's kind of a succession, community succession in the vent ecosystem. And this is in a way not similar, but analogous, maybe succession after wildfires. So in ecology, in different domains, actually, there are examples of these sort of things. So just also putting this around, maybe it's another collaboration axis, maybe these sort of things. All right. The eruption. After the eruption, they actually canceled the dives. It was too risky, and then the area needed to be mapped again. And we had 3 more days in the expedition, and there were also some talks with Woodsole and NSF. They said, okay, stay as much as you can. The ship will go faster on its way back. So I think in total, we spent 4 more days after the reaction. So we spent 2 more extra days in the station. And we did a lot of CTD casts. I mean, okay, Alvin wasn't available anymore, but we didn't stop there. So we took our electrochemical system and put it on the CTD rosette because it was really deployed over the eruption area. And we were in a way already experienced with the CTD application of our system because Barış talked about bridge Blacksea and Decosim as well. As a part of these projects, we have already developed the capacity of measuring in situ, for example, measuring hydrogen sulfide in situ in the Black Sea, for example, at elevated depths. So we immediately switched that mode. We changed our methodologies. This is, by the way, how the sensor response is in the Black Sea. These are some, again, raw data from our summer expedition last year. So we were able to document in really high sensitivity how sulfide builds up. And so we started doing that over the eruption area. Normally, these hydrothermal vents, they have a plume also associated with them, but they rise maybe a couple of 100 meters, then they disperse laterally. And in this case, actually, we found that using our sensor, we found that the signs of eruption, or at least the chemicals released from the eruption, were able to be detected as much as 600 meters above the plume. And this finding is also verified by other measurements. We had, for example, multi-beam, the water column mode of multi-beam also showed similar depth layers, and we also had turbidity measurements, etc. So altogether, we think that this eruption basically created a mega plume, which transformed the deep water chemistry in a really large area. But for me, it was the first time I saw, for example, hydrogen sulfide in a deep ocean, entirely oxic. This is deep Pacific, and essentially it was there. It wasn't decaying fast. That was really interesting. And yeah, now we are trying to put together different data sets. We also have maps, multi-beam maps of the eruption, and we deployed a camera system and towed it with the ship. We have photographs of the newly basically cooled lava, etc. So now we are putting all these things together, I think, as fast as we can to be able to share this finding with the rest of the community. Thank you once again. Yeah, this is it's an anemone actually. It's an old seafloor, not so old actually, maybe from the last eruption, but already there's some sediments above it. It's an anemone basically, which located itself in between a crack between basalt. Yeah, thank you. And